All right, this week we talk about local winds and thunderstorms. So we'll just move on to local winds here. They're typically you're going to find them a lot in the summertime. Many people think of sea breezes, lake breezes, even river breezes can have local winds. Uh, we have local winds in my area because I have a pretty large bay to the north, which has winds coming off of it like a sea breeze instead of the bay breeze. And sometimes we get local winds around the rivers. The James River, which runs just to the above my house, is almost 5 miles across right here. And then to the north of that is the York River, which is about 4 or 5 miles across as well. And in the summertime, you can actually see almost like a sea breeze set up between the two of them. So where the warm air rises over the peninsula between the two, and then the cold air comes in from the rivers towards that area and just helps cause circulation both directions there, almost like a peninsula effect would be in Florida with two sides of the circulation, just not as strong, but it can generate some thunderstorms in the summertime, and we've seen that happen here. So basically what you have during the summertime, you get the land heats up, and the air rises, and then the air from the water comes ashore, while aloft the air moves back towards the water. The greater the temperature contrast, the stronger that wind's going to be. And it can happen at night, just the opposite direction. One of the things a lot of times you're going to find uh, in the cooler oceans, particularly up to the north, up towards from Virginia Beach north even, where I am, in the springtime, a lot of times that contrast will be the strongest because the ocean gradually warms up a little bit. So you may actually get less of a sea breeze. If you were down over the Carolinas, for example, May is a real big month for sea breeze down there. It may go in pretty far. Further up, maybe over Maine, it may be more in the summertime where you get the ocean still cold and the land warms up really well during the summertime. Down over Florida, it's pretty much all year long. But the same token, you got to get the water does warm up down there some during the summertime, but the land is also quite hot. So you're getting sea breezes down in that area as well. And these sea breezes can generate thunderstorms. They do cause rising motion where they form over land. And if more than one sea breeze is around, they might intersect. You get that convergence, and you get even more rising motion. So mountain and valley breezes, on the other hand, are very difficult and can get very confusing. Uh, these typically develop in the summertime, more pronounced because wintertime you have more of a gradient wind flow. The morning sun on the mountain begins the whole process. Uh, Once it begins to heat one of the slopes on the mountain, that slope, the air starts to rise, and then the air comes in from another direction to take its place. So as the slope gets shaded, then that can affect the strength and duration of it. Uh, I've taken several fire weather courses, and in the western U.S., they have this down really well. They understand what's a slope, uh, how the sun will hit that slope, uh, and which direction the wind's going to blow, and then how that's going to impact that fire that day. And valley breezes can also, even lead to a thunderstorm development in the air is unstable. Mountain breezes at night where it's blowing down, slowly down slope, the cold air forms at the top of the mountain up there and gradually sinks because it's denser. So it's going to move down to the valley and help to aid in fog formation down in the valleys. Uh, Mountain waves or lee waves are common across parts of the Appalachians, also out in the western mountains, all over the place. They can occur out there as well. Uh, Appalachian Mountains, you get the strong northwest or west flow behind the cold front. That sets up a wave pattern. You can really see it many times in clouds that develop uh, just out to the eastern side of the mountains. And if you were to come in directly into one of these, circles, waves that develop, your aircraft could be in a lot of trouble very quickly. That's one thing. If you can come in further from the east, gradually building into the circulations, you can actually get a feel for how they're picking up and whether that's too much for you or not. These can also occur in the western mountains, particularly the Santa Ana winds, for example, out in California, coming down the mountain slope there. You're going to get wave patterns around that area. If you got good strong flow from the west into the mountains, maybe the deserts to the east of the mountains will have some of the wave patterns coming off of them. So we'll go on to another slide of this then. We'll start talking a little bit about the local winds today. There's not a lot around, but I thought there might be a few things. So what I did was I picked out, think about this cold front moving through the Appalachians right now. And this is, right around noon-ish on this Friday. And that cold front is going to be moving to the east later this afternoon. And when it does, there's going to be a decent northwest flow into the Appalachian Mountains. So let's take a look at that in terms of a model, how that model might depict the winds that develop with time. So if you do this, what I have here is a HRRR model. It's a high resolution model. And what I'm showing basically are the winds. And you'll see that they're color coded, from 0 to 10 miles per hour, or 10 knots actually, is, basically no color. From 10 to 20 has a light color, then a little darker color from 20 to 30, and, gradually going up from there. So let's put this in motion. And I want you to focus on the Appalachians. So we'll say right in here. You see a cold front, winds shift to the west right here. And they're slowly moving across. You still have a lot of southerly winds, and you'll notice local winds. Topography is playing a role here because you have much stronger winds out over the ocean. But notice these little circulations, almost stronger boundaries of winds picking up at different areas in the Appalachians and moving east. And then they're setting up right along to the east of the Appalachians here. There's a little area with the strongest winds. So you can actually pick out on these high resolution models sometimes areas that actually have an enhancement. So you can actually see where there's stronger winds blowing right along the surface, coming east there, another one back behind there a little bit. And this is not a real strong cold front, but it can actually show the wave pattern. You see, if you were flying along into this, you would have lighter winds picking up the stronger, lighter, stronger, gradually bitten through it on the other side of the mountains. But you can actually see a pattern, like a wave pattern to this. So let's take a look a little further west. This looked interesting to me because there's all kind of hills and valley systems out in California, in the southern part of California. And you can actually see here, you have some winds coming from the land down a mountainside here. That's the Santa Barbara Airport. You have southwest winds, 10 knots, whatever there. And that's right in here. Let's go up a little bit. And we're looking a little inland here, a little bit more. And all of a sudden we have north winds at 14 miles per hour, or 12 knots. And there's some gusts all the way up to 30 miles per hour. This is coming down a mountain range, down from the mountains in here. So you do have some local wind effects going on, even on a day when you wouldn't necessarily picture them happening. So really knowing the topography, knowing where the sun's hitting the slopes, where you may get lifting, whether you have strong enough winds to overcome them, or maybe the winds you got will actually enhance what you're looking at there. So you may wind up with stronger orographic effects, mountain waves, and all. So you've got to know the direction of your winds, what your topography you're flying over is, in order to understand what's happening. So let's look at another thing. We're moving on now to one of the topics I really kind of like, and we'll just get right into it. The thunderstorms. I spent lots of time looking back at thunderstorms. So we're going to try to go back here a minute. And we'll start with this. So thunderstorms can start from thermals. Uh, all that really is, a thermal is just a partial lifting from the heat at the ground, causing it to become unstable relative to the air right around it. And we've talked a lot about stability the last week or so, and you're going to continue hearing it. It's a key part of meteorology. So that just lifts that up. Same kind of thing can happen. Say the cold air is moving over warm water. If you were to fly over the Great Lakes this time of year, one of the things you would have would be just the opposite effect of very cold. You could have cold air hitting that water, but the water would still be cold as well. But stay early in the winter time when the water has been heated all summer long and you're just in the fall right now. Some of the first lake effect events have a lot of convection with them. The reason they do is the Great Lakes temperatures might be in the 40s, and the air temperatures that are coming into there are probably in the teens, even single digits. So you think about that. That air is warming that very lowest layer. That air is being warmed by the water just above it there, just underneath it, and lifting that air becomes warm enough. It starts lifting up. It's definitely warmer than the surrounding air, so it just keeps rising until eventually it has cooled enough and begins to precipitate, and you wind up with even some small thunderstorms in these things. And sometimes it's so violent that you actually get some little tornadoes spinning out over the water, almost like a dust devil. So these are just really classic examples of thermals. So this is a convective type of sounding. What this is a skew T. So yes, your temperatures are skewed. Instead of going straight up and down, they're skewed to the right. The dew points plotted as well. So if your temperatures and dew points are plotted along the skewed lines, dew points are in green, temperatures are in red. So you have the red temperature gradually warming up, little stable layer there. Continue cooling off here, cooling up. Let's go back. All right. So we'll play it from here again. And we have that temperature gradually warming up there. You can see the winds. What you'll notice is down at the bottom, we have a southerly wind very quickly turning. There's your wind shear to the southwest and increasing in speed. I mean, literally within 1,000 feet of the surface, you go from south to southwest from 10 knots to 30 knots. So, and other thing is to think about, okay, I'm lifting a parcel of air. So let's try to lift a parcel, we'll say right here. That parcel is going to be lifting from 900 and maybe 900 millibars, we'll say. So the air temperature at 900 millibars, it's around 20, a little bit over 20 degrees Celsius, we'll say. Dew point, about 15, 16 degrees Celsius. All right, so one of the things you do as you're lifting that air parcel is it's going to gradually lift up and lift up. So it's coming up a dry adiabat. And dry adiabats typically on these charts are almost to the left. So it's hitting, going up like this. Well, at some point here, it and the dew point are going to cross. And your temperature is going to get cool enough that it can't hold any more water. And it's going to be going up. When it does, it's going to start going up at the warm adiabat, which is this line right here. So that the air parcel is now much warmer all the way up with time. It gets up in here. The other thing to think about, what happens with all that moisture? Well, you look at this, how dry this sounding is right in this section here. Okay, well, if I throw moisture in there, what happens? Well, the temperature drops because the sounding is going to want to try to come together. The cloud's going to force this moisture to go to the right on the sounding and the temperature go to the left. So you wind up with a more unstable sounding. So that's one of the things that happens with it. This is a Doppler radar picture here. It was taken a number of years ago There's a couple hooks on this thing. You can actually see in thunderstorms here, there's a hook down here. Very nice circulation. And there's another one, a little tougher to spot down in here. I almost could say it's like a multi-hook, almost like a bow kind of thing. Lots of white indicating very intense convection. So there's very intense convection. So let's look to the right. You'll see the Doppler radar showing the velocities. You'll see you have velocity towards the radar here and away from the radar here. So you're actually showing a nice little circulation right in here. Right in here, you even have more intense, very intense velocities, which chime up very well with this part of the hook down in here where there isn't as much precip. So this is showing a very clear picture of that, the two possible tornadoes right there. So, life cycle of a thunderstorm. The book talks about it in clear detail, really. Starts off with the towering Q. Everything's going up initially in the initial phase. As that towering Q develops, begins to get cold enough, ice particles begin to form. Precipitation begins to develop aloft in it. Also, when ice particles form is when lightning can occur. You need ice particles for lightning. That is one of the things happens is ice particles kind of split when they initially form. That actually causes a charge differential, and that charge is what causes lightning. So if you see lightning occurring, you know that that thunderstorm has reached an altitude probably around -7 to -10 or more Celsius. Well, if it's reached that and you know what the morning sounding was, you know how high that cloud is. So you can take a good guess as to just how high that cloud is, even before you look at radar. So now that we've got precip developing, we're going to transition. That precip's going to have a push down effect. You've also made the air colder somewhere there. It may become more stable, so it begins to lower and drop down towards the ground. So you get a downdraft beginning. And as that downdraft hits the ground, it begins to spread out, push away from it. If it goes big enough, if it goes out far enough, it might actually limit any more warm air coming up or rising up. Instead, you have that cold air at the surface, so you won't get any of that rising motion. So you wind up instead cutting off that thunderstorm source of warm air and the unstable air it had, and it begins to die. So some things can change that, and one of the things that really changes it is wind shear. I had a professor once that told me wind shear is what modulates a thunderstorm, and it's true. Air mass thunderstorms typically have light wind shear. Not a lot of winds aloft, not a lot of winds at the surface. Storm cells are just kind of propagating along very slowly. Might develop on sea breezes, mountain ranges, or just kind of pop up on warm spots that happen to develop. So you get the light, not much sea breeze blowing, or not much wind shear. So what you wind up with is, okay, with what we talked about, that outflow at the bottom begins to push out. It cuts off the warm air going up into that storm. So you wind up, instead of having a nice continual rising motion of unstable air, you wind up with all the air sinking, coming down. But one thing that does happen in air mass thunderstorms, all that air comes down and pushes out. Well, if there's another thunderstorm somewhere nearby, maybe those two thunderstorms, air mass downdrafts, come together. Where they do, you call it convergence. Thunderstorm might begin to develop there. It's actually something that's been looked at in forecasting thunderstorm development, and you can actually see it sometimes very clearly on satellite pictures. Multi-cell clusters form with stronger wind shear. You get a whole bunch of thunderstorms starting to develop. Now you're getting some organization to them. They're each helping each other. Each storm is working to help the others. And one storm may be decaying, one storm may be growing, with other ones meets its mature stage. They're all in different phases. And sometimes I know that airlines and air traffic controllers and sometimes will try to route airplanes through the different sections of that multi-cell that might be a weaker stage, so they can get people by that area if they can't get around the storms. But the more wind shear, what happens is you get that wind shear, you wind up holding that updraft so that it stays more directly under the storm. It doesn't push as far out in front of it, even though it can be very strong, but you're getting a lot more warm air going up then. And then supercells typically have very strong wind shear. One of the things they also may have a rotation to it. We were looking at that last sounding, and what we had is southerly winds at the bottom, shifting to the southwest and even to the west aloft. Well, they're turning with height, so that causes a rotation of the air. So something to think about when you're looking at storms. Is there a good rotation? And here's a photograph which actually showed that really well. Every 1,000 feet, there's a plot on here. And you can actually see that at the surface, we talked about 10 knots of wind. Right above the surface, there's 25 knots of wind. Then right above that, there's 30 knots of wind. Then there's over to 40 knots of wind. But look how it's changed direction. Southerly winds, southwest winds, west winds. So the thing is actually made almost like a circle in this photograph with time. And that's one of the things you like to look for, particularly in the lowest 6 kilometers. So if every kilometer is plotted at the lowest 6 kilometers, you wind up seeing the rotation, how they turn. And if they turn and get winds up to around 40 to 45 mile an hour, you might get really potential for tornadoes to develop. Multi-cells, you're probably looking at wind shear at least 30 knots to 40 knots. If you want severe, probably over 40 knots. So that you wind up getting, you can have straight line. Everything could be coming out of the south. And if by the time you get to 6 kilometers, it's moving over 40 knots, there is the potential for severe downburst, hail with that storm. By the same token, if you were to take that same line and curve it, and the wind shear wind up over to 40 or 50 knots over here, well then, yeah, you're getting the other effect of possible tornadoes. And some of the really super ones, you'll see the wind shear literally go all the way over to 60 to 70 knots, and a very steep, very strong curve. So you really can see the rotation in it. Some hazards in the thunderstorm, obviously wind gusts, multiple directions. Some of these wind gusts in a derecho, for example, can be well over 100 miles per hour, and these have been observed well out ahead of the storm. There was a derecho a few years ago that came down, developed to the northwest of Chicago, came across West Virginia and across Virginia. Some of the wind gusts in that storm were well over 90 to 100 mile an hour, and they were way out ahead of the thunderstorms. Thunderstorms were like 20 to 30 miles behind the initial line of winds that was moving through. So you wound up getting the very strong winds, and then about 15, 20 minutes later, the thunderstorms would arrive. So it was an interesting way that these kind of wind gusts can occur. So it's something when you're flying into an airport or whatever that you need to be aware of as well, to see how the winds might be gusting and affecting your flight. Tornadoes, they form in what they call a supercell, where the supercell means there's rotation aloft. If you have, and many thunderstorms do have rotation aloft. You'll see it when you're looking at and analyzing thunderstorms, that there's rotation all over the place some days, and lots of storms. Not every one of those storms, however, is going to produce a tornado. And that's where the differentiation begins, to try to figure out which ones are going to do it, which ones are not. Sometimes it's easy to see that, oh, you have this rotation maybe at 15, 18,000 feet up. All of a sudden, you're starting to see it down at 6,000, maybe down at 4,000, and it's lowering. That's when you know that there's probably a tornado developing there, and it's going to come down to the ground. And there'll be other times where you can see the rotation just gradually weakening, and it just stayed aloft. So these are things we, as meteorologists, you look at in thunderstorms. You can actually see it in the radar. You have access to nowadays. You also get hail in thunderstorms. Obviously, their updrafts must be quite strong for that to happen. And there's got to be some cold air aloft. In the middle of summertime, you're not going to get a lot of hail. If you're in Florida, you're not going to get a lot of hail because your thunderstorms are relatively warm, big warm layer to go through for that hail to form. However, if you're out in the Midwest, for example, or up in the Rocky Mountain area, you can get tremendous hailstorms. Sometimes hail can be up to over several feet deep in hail. The hail may be only an inch to 2 inches around, but it causes a lot of damage just because there's so much hail. Lightning, there's tremendous lightning networks out there right now. One of them actually down at Cape Canaveral, area. There's a lightning detection network that's deployed down there. That picks up any stroke of lightning, either going up, going down, and what it looks at is, you watch a lightning strike, you can see kind of all different kind of fingers of lightning coming out of it. Each one of those is identified in that lightning detection network as a new strike of lightning. So you wind up with lots and lots of lightning showing up. There's something to think about when you can. Those kind of networks are gradually expanding as well. There's one in the Washington, D.C. area. They're developing one for Wallops Island for the thunder, where they're doing some space flights there. There's one in Huntsville, Alabama area. So they'll be gradually, you'll see more and more of those. While there's what they call the National Lightning Detection Network, but all it does is pick up cloud to ground strokes. These other lightning networks will pick up cloud to cloud strokes as well, which can be valuable. One of the other things that's been learned here, when you really look at that kind of lightning data in detail, it might indicate the possibility of severe weather. One of the things that's been pointed out is there's typically a lightning jump. What they mean by that is that lightning increases rapidly and then all of a sudden starts falling, becomes much less. What that means is an updraft really developed, got really strong, caused a lot of charge separation up and lost in the clouds, so a lot of lightning was forming to release, get rid of that difference of charges, and then as it gradually stopped going up so fast, it starts coming back down. You wind up with this push of very cold, dense air being pushed back towards the surface, very stable air. It's rising, moving very fast now down towards the ground. So you wind up with a very strong downburst, maybe a large hail. So just some things in the future of lightning as well being looked at. GOES 16 is now coming online this fall. That will be able to detect lightning all over the U.S. and the surrounding oceans. You'll get a very detailed picture of lightning. And that's any kind of lightning, not just cloud to ground, but also within cloud as well. The Storm Prediction Center has tons of information, convective outlooks, and on severe weather. So it's just something to look at also. And there's some instability charts. We're going to look at some other one of these a little bit more detail. Also, the Storm Prediction Center collaborates literally with the Air Weather Center in Kansas City on their convective outlooks that they issue. And there's a convective outlook that Kansas City issues as well hourly. We're literally concerned with when convection will develop, where it might develop. That can be used by the pilots as well. So we'll take a look at Storm Prediction Center today as well. You'll notice that there's a marginal risk of severe, and even a slight risk of severe over southeast Virginia, northeast North Carolina. They've actually issued now a mesoscale discussion about that. So what they're looking at here is like a warm front. Notice the dew points down here, 63, 65 coming up to this area here. And you still have a northeast wind here. What happens in the Appalachians is you wind up with these highs up over New England that are pushing air in from the northeast, and they hit the mountains, and they cause the pressure to rise. And that just stalls, makes it very hard for these warm fronts to lift north. So right along that boundary is where the potential for severe weather might be, and that's what that's indicating. They're just looking at a residual wedge there, outflow boundaries in that area, North Carolina, Virginia border, and they're looking at the temperatures now in the 70s to the south of that boundary, 74, 75, 76, and dew point air in the mid-60s as well. So that's going to start lifting updrafts. There's a strong southwesterly low to mid-level flow of 40 to 55 knots, which will help organize it. There's your wind shear. So this is not a major event. It's marginally severe hail. Gusty winds are possible as these storms move east later this afternoon. So we'll take a look at some of that a little bit here in the Storm Prediction Center as well. I wanted to look at a couple other things with the Storm Prediction Center too today. So we'll go back to the home page here because I really wanted to start right there. There's amazing looking at the climate. Severe weather climatology per day. So today, for example, this is the chance that you would have of severe weather within a 25-mile square. So if you were in Oklahoma, Arkansas today, you actually have a 30 to 40%, 3 to 4% chance of seeing severe weather on this day. Notice how small it is, even over towards where around a 1% chance, or down in Florida is a 1% chance. So it's just something to look at, to think about when you're looking at this, that you got probabilities literally with climate. And one of the other ones you can look at, there's your probability of tornadoes for the day. There's your wind damage probabilities, hail probabilities, significant tornado probabilities for today. All these are based on 30 years worth of, from 1982 to 2011 climatologies. So it's just interesting to see, what they're looking at, how they're seeing things with it, and knowing your climate. Is this a day where you would expect, tornadoes or whatever in your area? So we'll look a little bit more at Storm Prediction Center here. So let's look at some upper air charts today, since we've been dealing with the potential for severe weather, we're outlooked. So let's see what's going on a little bit. Well, let's see, we're back. Let's go back here a minute. All right. Here's your strong jet coming up through the Midwest. When we talk about jets, we've talked about them before. To the left-hand side is where the divergence is aloft, so you've got lift aloft here. And also where the jet's down in here, you have some lift on the other side. You can actually see a southern jet kind of moving off to the east, and same up here as well. So if you go back in time, let's look it down at 500 millibars a little bit. Have your 500 millibar low, mid-level of the atmosphere, remember about 18,000 feet. A little bit of a jet out in here as well. So you're looking at, low pressure, probably somewhere Ohio, Indiana at this time frame. Very strong upper low coming into California as well. So you get something out there. So you look at that. We'll look at some soundings with this as well. Let's take a look at Greensboro. Greensboro this morning had lots and lots of moisture until it got up to almost 500 millibars. Well, let's lift the parcel from down here, we'll say. If I do that, and it's going to moist adiabatic, it's going to go warm adiabatic lapse rate. Here's where the parcel is going to be going along this route. Its air temperature is going to be, its temperature, that parcel. And you'll notice that the actual environmental air is all cooler than that. So you wind up continuing to rise and accelerating. Well, now it's going to hit this area right here above 500 millibars, middle level of the atmosphere. Well, what's going to happen? We're going to introduce moisture into that area. Well, that moisture is going to take this temperature and move it over here. So instead of being a little bit unstable, it's going to become more unstable, so that air is going to want to rise even faster. Eventually, it's just going to rise right into this area where it really starts warming aloft, where the stratosphere is getting down to it, and that's going to stop it right there. So how much of a curve is there on this? Well, kind of funky. Looks like it's going all over the directions here, but it's not real strong. It gets up to about 40 to 50 knots of wind shear from the surface to aloft. So that's enough to, produce some possible damaging hail, damaging winds. So just something to look at in the sounding for the day. And again, this corresponds really well with that area we were just looking at as being outlooked. These are just climatologies of sounding as well, like precipitable water. That's a measure of how much moisture is in the air. Say you wanted to know what the Cape would be at different things. You could actually say, there's the climatology for that as well. And you can see where, I have this much Cape. Well, then I'm, way, way more unstable than normal. Or I have way down in here, low, minimal amount of Cape. Well, I'm a lot more stable than normal. So we'll look a little bit more into Doppler radar as part of your talk about things today. So we're going to focus in down in this area and see if we see something that we can talk about a little bit, maybe in a storm. If not, I actually did a tape a long time ago that talked about Hurricane Matthew as it was coming up along the Florida coast. And I will play that as part of this recording this time so you can actually see a use for a lot of the thunderstorms and see how Doppler radar can look. So we'll look at the base. This will be the lowest elevation. Doppler radar goes out and scans at various elevations. The max is up to 19.5 degrees elevation, and the minimum is 0.5 degrees elevation. So we'll start at 0.5. We're going to run a loop. I'm going to enable my Adobe Player to work with this. And okay, well, let's zoom in down in the area that we were talking about first. We'll stop it. Back one. Let's take a look here. These are individual thunderstorms, and you can pick one out here, one here. They're just kind of popping up all over the place, but they're in that area where we saw we still had some north winds to the north, some south winds to the south, and lots of moisture coming up from the south. We also have aloft, cold air coming in aloft, which is going to help feed this area, make it more unstable with time, while the bottom layer stays fairly warm and moist for a while before that cold front gets through. So you wind up, these popcorn type thunderstorms all over this area right here. One here, almost like a line of them, little cluster of them developing there. So let's take a look at velocity a little bit. I don't think we're going to see much. Okay, when you're looking at velocity, sometimes it's hard to spot something, but see if we can pause this for a second. Move forward a few here. All right. We talk about rotation in a thunderstorm. Well, the radar we're looking at is over here. So you have a little stronger winds right here towards the radar, a little weaker back in here. You actually have a very weak circulation right in here, maybe at the end of this storm as well, a little bit. But then you got to remember also that this area is a little bit higher up. This is a little lower, so maybe that's contributing as well. Just things to think about if you're a meteorologist, you got to look at. One of the things you'll notice right along here, this is an area where the Doppler radar can't determine what wind direction is actually occurring. There's a lot of physics that goes into that. I won't talk about it, but just say that you can, as an operator of Doppler radar, you can adjust that line so it's down here, or it goes back towards the radar. It might go out a little bit further. So the operators have a choice of where that line shows up. Right now, they're allowing it to occur right here. So you can actually see, little circulations, again, moving forward through this. Maybe a little bit of one right in here as well. Nothing very strong. Wind gusts probably only upwards of 20, 25 miles an hour with some of these storms. So All right, so we'll take a look. One other thing, 1 hour rainfall, great way to estimate how strong the rain is occurring. You can see these bands here develop with time. It actually shows the direction of motion of the storm, and there's more rainfall that occurs. So, but now we'll let this other tape flow a minute. I'm going to pause everything right here, and we'll see if we can work this out. Yep, I couldn't stop with one recording this week. I wanted to talk a little bit about radar and the hurricane. Here's Matthew this morning, right off of Daytona Beach. Daytona Beach is about right there. Here's the eye, very circular, well formed in the radar image. You can see the most intense bands are just offshore. They just barely nick the coast when they come around. So that the strongest winds are probably on the east side of the storm, which is very typical for a hurricane. They're probably where you would find the maximum winds for this hurricane. However, some of the stronger winds are barely nicking the coast or coming in as well. So this is a loop over a short period of time, and you can see the rain bands. One of the things about a hurricane is there's different bands with it. You can see one band up here. You can see the eye wall here. You can see another band to the south of the storm. There's not as much precipitation to the south of the storm. We can take a different look at this. Here's Jacksonville's radar, and you can see, again, there's a lot of band structure. There's one that develops out here to the north of the one. There's another one. Here's another band swinging back around here. Another one up here. That's one of the interesting things. It almost seems like you're in showers when you're in a tropical system, because you'll get one very intense rain event, then it'll let up a little bit, then it gets very intense again. So each one as they're coming through. But this is the reflectivity from the radars. So let's take a look now. We'll move over to velocity. This is the velocity estimate. It's very difficult in a hurricane to determine just how strong the winds are, but looking at this, you're probably getting up to 99, 100, over 100 mile an hour winds at this elevation, which is not that high up, right out in here. Probably just maybe 3,000 or 4,000 feet in the atmosphere. So just off the surface, here's some very strong north winds as well, just coming into the coast here, probably in the neighborhood of 60 to 80 mile an hour winds as well, right in this area. These are not gusts; these are sustained winds. So they would feel like they would be blowing constantly at this speed, whereas a gust is very short-lived. Usually you get a little bit stronger gust. But this can actually show very nicely where there's almost no wind whatsoever in the center of the storm. Any stronger circulations out just around the eye wall here. You'll notice this zero line right here says there's no wind. With the Doppler effect, when you're right along the line with the wind direction the wind is blowing, Doppler can't see it. It thinks it's zero. So in this case, right along this line, the winds are blowing from the east. So Doppler thinks you have zero wind there. The same would hold down here. It's blowing from the west. Doppler would say, oh, I can't see that. So it's zero wind as well. So this is a good way to determine the wind direction of a storm within it. The next image I'm going to show is just the storm total precipitation, and you can see some remarkable totals of rainfall. Over 12 inches offshore of Daytona Beach, Cape Canaveral. However, there is some intense bands that obviously have come ashore with very heavy rainfall. Here's over 8 inches, almost 10 inches of rain since this storm began in this area of Florida, just to the north of Orlando, coming down. So this is another thing that Doppler radar provides, which is a very good estimate of rainfall as well. You can look at the national views as well on these things and see the whole country. You can see where the rain is all along the East Coast. A lot of this just being caused with Matthew coming up, pulling moisture in off of the Atlantic Ocean. You can see another system coming onshore in the northwest. So it's very useful to composite all these rainfall estimates and reflectivities from radar. You get a good look at how everything goes in the atmosphere and works together. Okay, I don't know how that last part turned out, but we'll just finish up right here quick. You can see This is a composite radar. So this is taking the maximum reflectivity DVZs at any elevation that the radar has scanned. So that's from 0.5 degrees all the way up to 19.5 degrees. So you can pick out a little bit of enhanced precipitation right here as it's coming east, and each one of these little storms as well. So let me know if you have any questions this week, and we'll be talking to you later.